Hi all, see this particular problem talk about that you have to go ahead and find out this series, okay, or you can say that it's a infinite series because n tends to infinity, right, where that alpha beta is actually root of a quadratic equation. So let's first observe the infinite series here, right? So let's consider that series as S, right, because it is easy to go ahead then. So let us consider that S is equal to limit n tends to infinity summation of r is equal to 1 to n alpha to the power r, plus we have the again the same limit n tends to infinity summation of r is equal to 1 to n beta to the power r. Okay. Now see that here generally to find the infinite series or in the series if the limit is present, right, our technique should be, right, first you need to calculate the series and then we need to apply it. But as we see that n doesn't have any problems here, right, because you can apply that, and in other way whatever there inside that series, right, it forms a GP, right, because see that it's alpha, alpha square, alpha cube and so on, right, similarly for here. So we just say that directly that this can be equal to summation r is equal to 1 to infinity alpha to the power r plus summation r is 1 to infinity beta to the power r. So basically this came as a two series where is alpha plus alpha square and so on, and obviously for the second case we have that beta plus beta to the power beta square actually, sorry, and that's it. Okay, now these two, okay, are actually a GP series. So this is a GP series with first term alpha and common ratio alpha again. Okay, so I write down in that form. So here the first pair is represent that first term and the second pair is represent the common ratio. Okay, and for the second one also we can say that it's again a GP with first term beta and common ratio again beta. Okay, that's it. Now see that here that first these two series is actually infinite GP series, right? So we can know that how was the formula for adding infinite GP series. So if I add that together, we'll get that 1a divided by 1 minus r. So that's why we'll get it as 1 minus alpha plus beta divided by 1 minus beta. Okay, let's add them together now. So therefore we can see that my S is became let's take that. So 1 minus alpha into 1 minus beta is actually the LCM, and if I multiply we get it as alpha into 1 minus beta plus beta into 1 minus alpha. Let's multiply that. Okay, so we'll get that 1 minus alpha minus beta, so we write down as minus alpha plus alpha beta obviously, and here we get alpha plus beta obviously. I just rearrange these terms and we get it as minus 2 alpha beta. That's it. So that gives me the alpha beta and all that stuff. Now see that, right, here alpha plus beta and these values can be easily obtained from this quadratic equation using sum and product of the roots. So here we'll say that alpha comma beta are the roots of the quadratic equation 375x square minus 25 x minus 2, and that's equal to 0. That's imply that sum of the roots alpha plus beta is equal to 25 divided by 375, and the product of the roots alpha beta is equal to 2 divided by 375. Obviously we have a minus sign here. Now we just need to put it in this given form. So therefore S is equal to, let's substitute appropriate values. So you'll see that 25 divided by 375 plus 2 divided by 375 multiplied by 2. So that's why I change it here itself as 4. Then we have 1 minus 25 divided by 375 minus 2 divided by 375. That's it. So we can multiply the denominator and numerator by 375. So we'll get it as 25 plus 4 divided by 375 minus 25 minus 22. So therefore we'll say it as 29 divided by 348. This is 7, yeah. So that gives me as 1 by 12. So that's it. So therefore, for this problem, the summation value is actually 1 by 12, and that's it. So the first important phenomena to understand this problem, that this is a infinite GP series, okay? So they are represent that infinite GP series in a summation form. That's the only problem in this particular exercise, okay? Hope you understood it. Thank you.